Hi students, have a nice day. In this section we are going to discuss about the equilibrium in chemical process, a dynamic equilibrium. In the last section we have seen that physical equilibrium established in the physical state. So here we consider the chemical process, chemical reaction. For that we consider a general reaction A and B. A and B are reactants, C and D are products. So A combines with B will form C and D. Okay. And that C and D combines, that is C and D decomposes gives A and B. When the rate of the forward reaction, this is a forward reaction. Forward reaction. This is a backward reaction. So here the forward and the backward reaction takes place. When the rate of the forward reaction becomes equal to rate of the backward reaction, an equilibrium is established. An equilibrium state is reached. Okay, once again, we consider a general reaction, general process. A combines with B forms C and D. And after some time, an equilibrium is reached. How the equilibrium is reached? As C and D decomposes gives A and B. The rate of the forward reaction becomes equal to rate of the backward reaction. An equilibrium state is reached or an equilibrium is established. Initially, the concentration of A and B is maximum, isn't it? Before starting the reaction or initially, the amount of A and B is maximum. So let's represent it by a graph. Okay. So the concentration, here we consider the concentration. Here we consider the time. Initially, the amount of A and B are maximum, and when the reaction starts, the amount of A and B are decreases and reaches a minimum. This is A or B. And after, if the reaction starts, the amount of C and D increases. Initially the amount of C and D is 0. So C and D are increases. This is a C or D. And this is the equilibrium state. Okay. After reaching the equilibrium, the rate of the forward reaction and the backward reaction are the same. When the rate of backward and the forward reaction is same, we can say that it reaches an equilibrium. Are you clear? So this is a chemical equilibrium. And again we consider another reaction, a chemical reaction N2 gas plus 3NH2 gas, 3H2 gas. 3H2 gas gives a 2NH3 gas. And ammonia gas decomposes gives nitrogen and hydrogen. Okay, once again, N2 gas combines with the H2 gas will form ammonia gas. And that ammonia decomposes gives nitrogen and hydrogen. Okay. Initially the concentration of nitrogen and hydrogen is maximum. This also we are represented by a graph. We consider here molar concentration. Molar concentration. Concentration is shortly written as CONC, superscript N, concentration. So initially the concentration of nitrogen is, suppose the nitrogen is up to here. And hydrogen, the molar concentration, number of moles is 3. So hydrogen is more than that of nitrogen. Initial time. And what about the initial concentration of ammonia? 0. Okay, at a time is equal to 0, the concentration of ammonia is equal to 0. And when the reaction starts, the molar concentration of nitrogen decreases. Similarly, the molar concentration of hydrogen decreases. At the same time, the molar concentration of ammonia increases. Okay, so here an equilibrium is established. Equilibrium. So when reaching the equilibrium, the concentration of or the molar concentration of reactants and products are constant. Oh, look at this. Okay, also that graph. After reaching the equilibrium, the molar concentration of reactants and product are constant. It doesn't change. Here also, initially the concentration of nitrogen. Okay, I write here N2. 1 second. This is H2 reactant. This is N2 reactant. This is NS3 products, PDTS. Okay, reactant products. Initially the concentration of reactants are maximum. Okay, is maximum. When time passes, the concentration of reactant decreases. Here also the concentration of reactant decreases. Then product increases. After some time, the concentration doesn't change. The concentration of reactants and product doesn't change. That means the equilibrium is established. And remember that at equilibrium, the reactions not stops. The reactions are going on. But the rate of the forward reaction becomes equal to rate of the backward reaction. How we have to prove this? We prove this by taking deuterium, an isotopic study. A deuterium, an isotope of hydrogen instead of hydrogen moles. Okay, hydrogen molecule. Okay, we'll explain how to prove this is an dynamic equilibrium. Okay, so what is the reactants and product in this mixture, reaction equilibrium mixture? Here the equilibrium mixture contains N2, H2 and NH3. Okay, N2, H2 and NH3. Then by taking deuterium, instead of hydrogen we take deuterium. What are the products and reactants? N2, D2 and ND3. Isn't it? Instead of hydrogen, we take deuterium, an isotope of hydrogen. So this is an equilibrium mixture. N2, H2 and NS3 are there. And another case, N2, D2 and ND3. By mixing these two equilibrium mixture, okay, by mixing these two equilibrium mixture, if there is no reaction, we get N2, then H2 and D2, NS3 and ND3. But experimentally, the mixture contains N2, H2, D2, NS3, ND3, HD, NH2D, NHD2. Okay, that means at equilibrium the reactions are going on, but the rate of the forward reaction and the rate of the backward reaction is same. Okay, once again I explain this experiment. We have to prove the equilibrium is dynamic in nature. That means at equilibrium the reactions are going on. For that, first we take the equilibrium mixture N2, H2 and NS3, this mixture. Okay, and another equilibrium mixture. Instead of hydrogen, we take deuterium, an isotope of hydrogen. Isotopic study. Then in that mixture N2, D2 and ND3. Okay, instead of hydrogen you take D2, you get N2, D2 to ND3. And by mixing these two equilibrium, okay, by mixing these two equilibrium, if there is no reaction, what are the reactants and product in that mixture? N2, H2 and D2, NH3 and ND3. If there is no reaction, we can observe that all these reactants and product in that mixture. But by experiments, okay, in that experiment, the substance, the product and reactants are present in the mixture are N2. N2 is already there. H2, D2, NH3, ND3. And in addition to these products, in addition, HD, hydrogen and deuterium combines. HD is formed. Then NH2D, NH3 and deuterium combines. So NH2D. Are you clear? And again the one more reaction, NH3 combines with the 2 deuterium, NHD2. Or ND3 combines with the hydrogen forms NH2D, NHD2. This reveals that, this reaction reveals that at equilibrium reactions are going on. But the concentration of the molar concentration of the reactants and product are constant. Okay, the concentration of the reactants and product are constant. It doesn't change, but reactions are going on. Okay, so finally we can conclude that at equilibrium the reactions are going on, but the rate of the forward reaction becomes equal to rate of the backward reaction. Are you clear? So please read this experiment. It is given in your textbook. Yes, next we discuss some characteristics of equilibrium. First point is equilibrium is dynamic in nature. Chemical equilibrium is dynamic in nature. That means the rate of the forward reaction becomes equal to rate of the backward reaction. However, at equilibrium, the reactions are taking place. Second important point is the chemical equilibrium is established in closed system. Okay, chemical equilibrium established only in the closed system. Third important point is at equilibrium the observed properties are constant. That means molar concentration of reactants and product are constant, but reactions are going on. Okay, that's very important thing. And another point is the equilibrium can be attained in either direction, from reactants to product side or from the product side into the reactant side. That means once we have seen a reaction, N2 gas plus 3H2 gas will form ammonia, NH3 gas, and that ammonia decomposes gives N2 and H2. This is one of the equilibrium. It is in the forward direction. And it can be, this equilibrium can be achieved when we take ammonia, NH3 gas, and decomposes gives N2 plus 3H2 gas. Okay, in the reverse direction. In the forward direction we established the equilibrium, and in the reverse direction we established the same equilibrium. So it concludes that equilibrium can be attained in any direction. Okay, either direction. One more example, H2 and I2. H2 gas plus I2 gas gives 2HI gas. You know that equilibrium is represented by two half arrows in the opposite direction. Okay, already we discussed. I gas. Then this equilibrium is attained to HI gas. HI gas you take and kept in a closed vessel, we get H2 gas plus I2 gas. Okay. So equilibrium can be attained in any direction and is represented by a graph. Okay, it can be represented by a graph. Here we consider molar concentration of reactants and products. Here in this x-axis time coordinates or equilibrium. Okay, equilibrium by considering the time. In the first case, the hydrogen and iodine combines to form HI. Okay, this is for H2 or I2. And what happens in the case of HI? Initially the HI is 0 and then the amount of HI increases. Okay, the amount of HI increases. Okay, this is an equilibrium is established. An equilibrium established at this stage. In the second case, we take HI. Okay, we take HI. That HI decomposes gives H2 and I2. This is HI graph. This is H2 or I2 graph. Initially, here also molar concentration in the second case. HI decomposes gives hydrogen and iodine. After some time, equilibrium is attained. At equilibrium, the molar concentration of H2, I2 and HI are constant. Okay, it's constant. That means the concentration doesn't change, but reactions are taking place. H2 and I2 combines to form HI. HI decomposes gives H2 and I2. So equilibrium can be attained from either direction, from reactant side to product or from product side into the reactants. Okay, that is another important characteristics of chemical equilibrium. It can be attained in any direction. And the other important point is catalyst doesn't change the equilibrium. Catalyst, the substance which alter the rate of the reaction without involving it. Catalyst doesn't change the equilibrium, but it helps to reach the equilibrium earlier. Okay, please listen. Catalyst doesn't change the equilibrium, but catalyst helps to reach the equilibrium earlier. And in equilibrium, the free energy change. The free energy change is 0. Already we discussed in the thermodynamics. Delta G is equal to 0 at equilibrium. So these are the important characteristics of equilibrium. Yes, next we discuss law of mass action and the law of chemical equilibrium. First of all, law of mass action. Two Norwegian chemists, Gullberg and Weig, experimentally study large number of equilibrium reactions, and they generalized that the rate of the reaction is directly proportional to the product of molar concentration of the reactants. Once again, the rate of a reaction is directly proportional to the product of molar concentration of reactants. So let's consider a reaction. A plus B gives products. The reaction A plus B gives C plus D or products. According to law of mass action proposed by Guldberg and Weil in 1864, okay, large number of equilibrium reactions are studied by two Norwegian scientists, and they understand that the rate R is directly proportional to product of concentration of reactants. Product of concentration of reactants. The concentration is expressed in a square bracket. The concentration, molar concentration of substance is expressed in square bracket. And you remember that molar concentration of solids are unity. Okay, concentration of solids, it is 1. We consider as a unity. For gas and liquid state or in aqueous solution, the concentration we consider, and that concentration is represented by a square bracket. So the reactions takes place in liquid medium, the molar concentration we consider. Okay, and we can write that R is equal to K concentration of A into concentration of B. What is K? K is rate constant. Rate constant. K is rate constant. Are you clear? So a very simple concept, law of mass action. Why it is called a law of mass action? As earlier, the molar concentration is taken as mass of action. Okay, the molar concentration as earlier considered as mass action. Okay, the amount of substance in action, in reactions. That's why it is called a law of mass action. Are you clear? Yes. So molar concentration as earlier considered as a mass action. That's why the law is called a law of mass action. And a very simple concept, A plus B gives C plus D, rate is equal to K into concentration of A into concentration of B. As earlier, according to the definition, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactants. Clear? Yes. Then by this law of mass action, we can explain the law of chemical equilibrium. Okay, law of chemical equilibrium. So keep this in your mind. We move to the law of chemical equilibrium. By using law of mass action, we move to the law of chemical equilibrium. Okay, law of chemical equilibrium. Law of chemical equilibrium. Again we consider an equilibrium reaction. Here we consider an equilibrium reaction. A plus B gives C plus D, and a C plus D gives A plus B. This is a four-way reaction. Shortly I written FWD. This is backward reaction, BKD. Okay, you write full forward reaction and backward reaction. According to the law of mass action, the rate of forward reaction RF is equal to KF into concentration of A into concentration of B. Isn't it? This is reactance. The rate of a reaction is directly proportional to the product of molar concentration of reactants. So let's take as equation number 1. According to law of mass action, the rate of forward reaction RF is equal to KF. Equation is R is equal to K into concentration of reactants, product of reactants. So general equation can be applied here. And this is for forward reaction. forward reaction. We take the backward reaction. Backward reaction. In the case of backward reaction, C and D are reactants, isn't it? From C and D, AB is formed. So for backward reaction, the reactants are C and D. So rate of backward reaction RB. Rate of backward reaction RB is equal to KB. Okay, KB, concentration of C into concentration of D, equation number 2. For backward reaction, KB, concentration of C into concentration of D. Then at equilibrium, rate of the forward reaction becomes equal to rate of the backward reaction, isn't it? Rate of the forward reaction becomes equal to rate of the backward reaction. So equate these two equations. RF is equal to RB. Then equate the right hand side KF. Okay, KF, concentration of A into concentration of B is equal to RB. KB, concentration of C into concentration of D. Sorry, not B, it is D. Okay, from 1 and 2 we can write that KF, concentration of A into concentration of B is equal to KB, concentration of C and concentration of B. By rearranging this equation, KF, okay, KF divided by KB, the constant become in the same side. Then reactants and product in the same side. Concentration of C into concentration of D divided by concentration of A into concentration of B. A constant is divided by another constant, we get one another constant. So that is Kc. That is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Are you clear? Okay. And what is Kc? Kc is equilibrium constant. Kc is equilibrium constant. As earlier we studied one constant, that is rate constant. Small k is rate constant. Capital K is equilibrium constant. And the C denotes the molar concentration. Okay. Equilibrium constant by considering the molar concentration. When pressure comes, it is Kp. Okay, now we consider the molar concentration. That's why we can say that Kc. So what is Kc? Kc is the ratio of molar concentration of products to the product to the concentration of the reactants. It is a ratio. Kc is equal to ratio of molar concentration of products to molar concentration of the reactants. And very easy method to determine the equilibrium constant, Kc. Okay, now we consider another general reaction. Here the general reaction is A plus B gives C plus B. For another general reaction, okay, very simple, you go through it. Another reaction is A moles of A combines with the C moles of C, or A moles of A combines with the B moles of B gives C moles of C and D moles of D. What is the Kc? Okay, A moles of, as earlier we consider 1A, 1B. So here A moles of A plus B moles of B gives C moles of C plus D moles of D, and this is an equilibrium reaction. This is an equilibrium reaction. So for this equilibrium, Kc is equal to concentration of C raised to C. The stoichiometric coefficient becomes superscript. It's become power. Okay. Into concentration of D raised to D. Concentration of D raised to D divided by concentration of A raised to A. Concentration of B raised to B. So two equation, when we consider 1 mole of substance, Kc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. For this reaction, for this general reaction, A moles of A, read as A moles of A, B moles of B gives C moles of C plus D moles of D. Small letters, the stoichiometric coefficients. Capital letters, reactants and products. Okay, so this is Kc. Okay, so what is Kc? Equilibrium constant. Law of equilibrium. Okay, Kc is equilibrium constant. And when we consider a particular reaction, okay, now we consider a particular reaction, we have to write the equilibrium constants. So keep this equation in your mind, a very important equation for general reaction. This is the equilibrium constant. So another one, H2 plus I2. H2 gas plus I2 gas gives 2HI gas. Please write the equilibrium constant. Equilibrium constant Kc is equal to, by considering the general reaction, here only one product. Hi is the product. So concentration of Hi, the stoichiometric coefficient is 2. Okay, the stoichiometric coefficient is 2. Then no more product, only one product. Divided by, okay, divided by A. What is A? Concentration of H2 raised to 1. No need to write the 1. Okay, power 1 is already understood. Then the reactant B is iodine, I2. Again 1. So Kc for this reaction is concentration of Hi gas raised to 2 divided by concentration of H2 gas into concentration of I2 gas. This is for H2 plus I2 gives 2 Hi gas. Another reaction. Okay, one more we practice. Another reaction, N2 plus H2 gives NH3, N2 plus 3H2 gases. Okay, gas plus gas gives 2NH3 gas as equilibrium. Okay, what is Kc? What about the Kc for this reaction? Product ammonia gas. So concentration of NH3 gas raised to 2. Okay, the coefficient C raised to C. So coefficient NH3, the coefficient is 2, so 2 become power. Divided by reactants, concentration of N2 gas. The stoichiometric coefficient is 1. Now need to write there. And in the H2 gas, the power is 3 because of this stoichiometric coefficient. Okay, so this is about the equilibrium constant Kc. Next section we will discuss more about the equilibrium constant. Thank you.